Johannes Kepler represents a singular pivot point in human intellectual history, standing precisely where medieval mysticism met modern science. Born in 1571 in Weil der Stadt, Germany, he transformed astronomy from descriptive stargazing into predictive mathematical physics. His work demolished the 2,000-year assumption that celestial bodies moved in perfect circles, replacing it with ellipses. This revelation required abandoning aesthetic preferences for empirical truth, a conceptual leap that reshaped how humans understand evidence versus intuition. Kepler blended Platonic geometry, Lutheran theology, musical theory and rigorous mathematics into a unified vision of cosmic order. His religious conviction that God created an intelligible, mathematically structured universe drove him to decode what he believed were divine blueprints. Unlike purely observational astronomers, Kepler demanded physical explanations for why planets moved as they did, not merely how. This insistence on causation transformed astronomy from a mathematical tool into a branch of physics seeking underlying mechanisms. His 3 planetary laws became the foundation upon which Isaac Newton built universal gravitation, unifying terrestrial and celestial mechanics. Yet Kepler's full intellectual system extended far beyond these laws into harmonics, optics, theology, and geometric cosmology. Understanding Kepler requires examining both his groundbreaking empirical discoveries and the metaphysical framework that enabled them to emerge. Part 1. The Geometric Architecture of the Cosmos. Kepler's first major work, Mysterium Cosmographicum, published in 1596, proposed that planetary distances followed geometric necessity. He claimed that the 5 Platonic solids, nested within spheres, determined the spacing between the 6 known planets. These Platonic solids are the only 5 three-dimensional shapes constructed entirely from identical regular polygons, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. Kepler placed Earth's orbit as the reference sphere, then nested the dodecahedron outside it to define Mars's orbit. Outside Mars came the tetrahedron defining Jupiter, then the cube defining Saturn's outermost orbit in the known solar system. Inside Earth's orbit he placed the icosahedron to define Venus, then the octahedron for Mercury's innermost position. This arrangement explained 2 cosmic mysteries that obsessed him: why exactly 6 planets existed and why their distances followed specific ratios. The answer, Kepler believed, resided in the mathematical fact that only 5 Platonic solids can exist in 3-dimensional space. 5 solids created exactly 5 gaps between 6 planetary spheres, thus explaining the number of planets through geometric necessity. This was not numerology or idle mysticism, but an attempt at geometric causation using Euclidean proofs. The underlying assumption driving this model was that God, as the supreme geometer, designed creation following eternal mathematical archetypes. Geometry existed before physical creation, co-eternal with the divine mind, providing templates for the material universe's structure. Kepler wrote that geometry, being part of God's own nature, was implanted in humans as the image of God. This theological commitment meant that discovering geometric patterns in nature was literally reading God's thoughts made visible. The model contained profound philosophical implications about the relationship between mathematics and physical reality that still resonate today. Kepler assumed mathematics was not merely a descriptive language, but constitutive of reality itself, determining physical structure rather than just measuring it. This Platonic realism about mathematical objects contrasted sharply with the instrumentalist view that mathematical models were just computational conveniences. Most Copernicans treated heliocentrism as a useful calculating device, not a description of physical truth. Kepler insisted the Copernican system described actual physical reality, making him virtually the first true heliocentrist after Copernicus himself. His geometric model only worked if the Sun genuinely occupied the center, providing additional evidence for heliocentrism's physical truth. This move from instrumentalism to realism represented a crucial epistemological shift in how science relates models to reality. The Mysterium Cosmographicum model failed empirically. The predicted planetary distances did not match observations with sufficient accuracy for Kepler's standards. Using Tycho Brahe's unprecedentedly precise observational data, Kepler later discovered discrepancies of up to 10% in his predictions. Most astronomers would have accepted such approximations, but Kepler's commitment to finding exact truth prevented such compromise. Critically, Kepler never abandoned the core vision even after discovering his three laws and elliptical orbits. He published a second edition of Mysterium Cosmographicum in 1621, adding extensive footnotes explaining modifications required by his later discoveries. The polyhedral model persisted in his thinking because it addressed a question modern physics still cannot definitively answer. Why do planets orbit at their specific distances? Contemporary astrophysics attributes planetary spacing largely to historical contingency during solar system formation, not geometric necessity. This raises a fundamental question about explanation in science. Should theories explain merely how systems behave or why they must be structured exactly as they are? Kepler sought necessary geometric reasons. Modern science often settles for contingent historical accounts based on initial conditions. The intellectual influences shaping this geometric cosmology traced to ancient Pythagoreanism and Plato's Timaeus, which associated Platonic solids with classical elements. Medieval philosophers used these solids symbolically, but Kepler applied them literally as physical constraints determining planetary architecture. His Lutheran education emphasized that creation reflected divine rationality accessible through human reason, a theological foundation for scientific investigation. The natural light of reason, in Lutheran theology, allowed humans to discern God's plan in nature without requiring special revelation. This optimism about human intellectual access to cosmic structure contrasted with Reformed Protestant skepticism about reason corrupted by original sin. Kepler's confidence that geometry unlocked creation's secrets depended on believing human rationality genuinely participated in divine rationality. The polyhedral hypothesis also embodied assumptions about cosmic unity and coherence that pervaded Renaissance natural philosophy but have since fragmented. Kepler expected a single geometric principle to explain all planetary distances through one unified system. Modern physics has largely abandoned such architectonic ambitions, accepting that different domains may require different explanatory frameworks. Quantum mechanics and general relativity remain incompatible, suggesting nature may not reduce to one elegant mathematical structure after all. The search for a theory of everything in contemporary physics echoes Kepler's geometric vision, seeking mathematical principles that necessarily determine cosmic architecture. String theory posits tiny vibrating strings whose geometries determine particle properties, remarkably similar in spirit to Kepler's nested polyhedra. Kepler's geometric model also revealed tensions between aesthetic preferences and empirical accuracy that remain central to scientific methodology today. He initially preferred his nested solids because they were beautiful, simple, and theologically satisfying, not because data demanded them. When observations contradicted the model, he eventually prioritized empirical truth over geometric elegance, but only after exhaustive attempts at reconciliation. This struggle between mathematical beauty and observational adequacy persists in modern physics, where theories are often evaluated partly on aesthetic grounds. The concept of scientific beauty itself emerged partly from Kepler's conviction that God's creation must display mathematical elegance and harmonic proportions. Whether beauty constitutes genuine evidence for truth or merely psychological appeal remains philosophically contested in contemporary science. The Mysterium Cosmographicum established Kepler's reputation as a brilliant mathematician and secured him correspondence with Tycho Brahe and Galileo Galilei. Tycho recognized the model's ingenuity, but emphasized that only precise observational data could verify such claims, ultimately inviting Kepler to Prague. This collaboration between theory and observation proved transformative. Tycho's data provided the empirical foundation for Kepler's revolutionary laws of planetary motion. The model's failure to match observations precisely thus became productive failure, driving Kepler toward discoveries that actually did match nature exactly. Scientific progress often proceeds through such refined failures where increasingly accurate measurements force theory modification rather than wholesale abandonment. Part 2. The Three Laws of Planetary Motion. Kepler's three laws of planetary motion emerged over 20 years of exhaustive calculation, representing empirical precision, meeting theoretical creativity. The first two laws appeared in Astronomia Nova, published in 1609, while the third emerged in Harmonices Mundi 10 years later. These laws demolish the ancient assumption that celestial motion required perfect circles, replacing circular prejudice with elliptical reality. The first law states that planets orbit the Sun in elliptical paths with the Sun at one focus of the ellipse. An ellipse possesses two focal points rather than one centre, and the sum of distances from any point on the ellipse to both foci remains constant. Placing the Sun at one focus meant the other focus was empty space, violating the ancient principle that cosmic centres must be occupied. This asymmetry disturbed Kepler aesthetically, yet he submitted to what observations demanded regardless of philosophical comfort. The discovery emerged from his analysis of Mars, the planet Tycho assigned him specifically because its highly elliptical orbit made it most problematic for circular models. Tycho's observational accuracy reached approximately 2 minutes of arc, far exceeding previous measurements that tolerated errors of 10 minutes or more. Working with Mars data, Kepler initially attempted to fit the orbit using various combinations of circles and epicycles. He tried bisecting the eccentricity, adjusting equant points, and introducing new geometric mechanisms to preserve circular motion. After years of calculation, he achieved a model that matched observations to within 8 minutes of arc, which most astronomers would have accepted. However, Kepler famously refused to dismiss these 8 minutes, declaring that divine providence had given humanity Tycho's unprecedented precision for a reason. Those 8 minutes became the material for reforming all of astronomy because they proved circular orbits were fundamentally wrong. This decision to prioritize observational accuracy over theoretical elegance represented a methodological revolution in how science treats anomalies. Rather than adjusting theories minimally to accommodate data, Kepler reconceived the entire framework when systematic discrepancies appeared. The path to ellipses involved intermediate stages where Kepler tried various oval shapes before recognizing the ellipse's mathematical properties. He discovered that Mars moved faster when closer to the Sun and slower when farther away, violating the principle of uniform circular motion. This variable speed required explanation through physical causation rather than geometric convention, pushing astronomy toward physics. The second law addressed this variable speed by stating that a line from the Sun to a planet sweeps out equal areas in equal times. If you draw a triangle from the Sun to 2 consecutive positions of a planet separated by a fixed time interval, that triangle's area remains constant wherever the planet is in its orbit. Near the Sun, the planet travels a longer arc in the same time, creating a narrow triangle. Far from the Sun, it travels a shorter arc, creating a wide triangle. These triangles have equal areas because the increased distance from the Sun exactly compensates for the decreased arc length travelled. This law emerged from Kepler's physical intuition that some force emanating from the Sun drives planetary motion, weakening with distance. He initially formulated a distance law, where orbital speed was inversely proportional to distance from the Sun, which worked approximately for nearly circular orbits. Later, he refined this to the area law, which held exactly for all elliptical orbits, regardless of eccentricity. The area law implicitly contained what we now call conservation of angular momentum, though Kepler lacked that conceptual framework. His physical reasoning posited that the Sun rotates and emits species or fibers that push planets along their orbits like spokes of a rotating wheel. As planets move farther from the Sun, these fibers weaken, causing slower motion. Closer proximity strengthens the push, accelerating the planet. This quasi-magnetic force theory was empirically wrong but philosophically crucial because it insisted on physical mechanisms rather than pure geometry. The second law also resolved the ancient problem of relating time and position in planetary motion without complex geometric constructions. Ptolemaic astronomy required elaborate tables and computational procedures to determine where planets would appear at specific times. Kepler's area law provided an exact geometrical relationship connecting time to orbital position through simple area calculation. Though the mathematics remained challenging without calculus, the principle was conceptually elegant and physically meaningful. The third law states that the square of a planet's orbital period is proportional to the cube of its orbit's semi-major axis. The semi-major axis is half the longest diameter of the ellipse, effectively the average distance from the Sun over a complete orbit. Expressed mathematically, if period P is measured in Earth years and distance A in astronomical units, then P squared equals A cubed. For Earth, both values equal 1, so 1 squared equals 1 cubed, satisfying the relationship trivially. Mercury orbits at 0.39 astronomical units with a period of 0.24 years. Squaring the period gives 0.058, and cubing the distance gives 0.059, remarkably close. Saturn orbits at 9.54 astronomical units, with a period of 29.5 years. Squaring gives 870, cubing gives 870, confirming the law. Kepler discovered this third law on May 15, 1618, after years of searching for harmonic relationships between orbital periods and distances. He was pursuing the cosmic harmonies described in Harmonices Mundi when this mathematical relationship suddenly emerged from his calculations. The discovery filled him with joy because it confirmed his belief that God had structured the cosmos according to mathematical harmonies. He later wrote that the discovery was so overwhelming he thought he was dreaming when the numbers finally aligned. The third law revealed that larger orbits require disproportionately longer periods in a specific mathematical relationship, not an arbitrary one. A planet twice as far from the Sun takes not twice, but nearly 3 times as long to complete one orbit. This relationship held for all 6 known planets, and later proved valid for Jupiter's moons, Saturn's moons, and eventually all gravitationally bound systems. However, Kepler's formulation lacked one crucial element that Isaac Newton later added: the masses of the bodies involved. Newton's reformulation showed that the relationship actually depends on the sum of the masses of the central body and the orbiting body. For the solar system, planetary masses are negligible compared to the Sun, making Kepler's simpler formulation extremely accurate. But for binary star systems where masses are comparable, Newton's correction becomes essential for accurate predictions. The 3 laws collectively transformed astronomy from a branch of mathematics concerned with geometric models into celestial physics seeking physical causes. Kepler repeatedly described his work as celestial physics and an excursion into Aristotelian metaphysics, signalling his intention to explain motion physically. Ancient and medieval astronomy had treated planetary models as purely computational devices for predicting appearances without claiming physical truth. Kepler insisted his ellipses and variable speeds described actual physical motions, not merely convenient calculations. This realist stance toward astronomical theory created tension with instrumentalists who viewed all models as equally fictional if they predicted observations adequately. The Copernican controversy partly involved this philosophical dispute. Was heliocentrism merely useful or actually true? Kepler's commitment to physical realism made him defend heliocentrism as literal truth, ultimately proven correct. The laws also embodied a methodological commitment to mathematical exactness that distinguished Kepler from predecessors tolerating approximations. Medieval astronomy accepted that models would always involve some error, treating close agreement as sufficient for practical purposes. Kepler demanded that theory match observation with no systematic discrepancies beyond measurement error, raising standards for what counted as scientific success. This perfectionism stemmed partly from his theological conviction that God's creation must be exactly ordered, not approximately arranged. If the cosmos reflected divine rationality, then human reason should be able to discover its precise mathematical structure without residual fuzziness. Any persistent discrepancy between theory and observation indicated incomplete understanding, not acceptable approximation. The empirical foundation for all three laws rested entirely on Tycho Brahe's observational data, accumulated over 3 decades of naked-eye measurements. Tycho built custom instruments, achieving unprecedented angular resolution without telescopes, which were only invented during Kepler's career. His measurements recorded planetary positions typically accurate to within 2 minutes of arc under favourable conditions. This precision proved essential because the difference between circular and elliptical orbits only becomes detectable with such accuracy. Kepler's access to this data was somewhat accidental and contentious. Tycho guarded his observations jealously as proprietary intellectual property. When Tycho died in 1601, Kepler inherited his position as imperial mathematician and gained full access to the data. Without Tycho's measurements, Kepler's theoretical creativity would have lacked the empirical constraints necessary to discover the true laws. This partnership between meticulous observation and mathematical theorizing established a model for productive collaboration in science. The conceptual obstacles Kepler overcame in discovering elliptical orbits reveal deep psychological and philosophical barriers in scientific thinking. Circular motion had dominated cosmology for 2 millennia because circles seemed perfect, simple, and divinely appropriate for celestial realms. Aristotle argued that circular motion was natural for celestial bodies because circles, being endless and without beginning, matched heavenly perfection. Ptolemy, Copernicus, and even Galileo maintained this circular prejudice despite various difficulties it created. Kepler's willingness to abandon circles demonstrates intellectual courage because it required rejecting deeply entrenched aesthetic and metaphysical commitments. He later wrote that giving up circular orbits felt like abandoning a sacred principle. Yet empirical truth demanded the sacrifice. This tension between aesthetic ideals and empirical reality remains central to scientific methodology today. Physicists still debate whether mathematical beauty and simplicity constitute genuine evidence for theories or merely psychological preferences. Modern physics has repeatedly discovered that nature violates human aesthetic expectations, from quantum uncertainty to space-time curvature. Kepler's example shows that scientific progress sometimes requires abandoning beautiful ideas when observations contradict them, however reluctantly. Yet his search for harmonic relationships also demonstrates that aesthetic intuitions sometimes lead to genuine discoveries when mathematical beauty aligns with physical truth. The third law emerged precisely from pursuing harmonic proportions that Kepler found aesthetically compelling before empirical confirmation. The three laws raised immediate questions about why planets follow these specific patterns rather than others. Ancient circular models at least had philosophical justification. Circles were perfect, and celestial regions were perfect. Therefore, celestial motion was circular. But why ellipses specifically, and why the area law relating time to position, and why the 3/2 power law relating period to distance? These questions demanded physical explanations that Kepler attempted to provide through his solar force theory, though incompletely. Only Isaac Newton, working 70 years later, provided the complete physical explanation by showing that an inverse square gravitational force produces exactly these orbital patterns. Newton proved mathematically that any inverse square force necessarily generates conic section orbits, ellipses, parabolas, or hyperbolas, depending on the orbital energy. Kepler's laws thus became derivable consequences of more fundamental physical principles rather than empirical generalizations without deeper explanation. This progression from phenomenological laws to deeper theoretical foundations exemplifies how science advances through layers of explanation. Kepler described how planets move. Newton explained why they move that way through gravitational attraction. Einstein later explained gravity through space-time curvature. Each level provides deeper insight while preserving the empirical accuracy of previous descriptions at their appropriate scales. The laws also enabled unprecedented predictive power for astronomical calculations and became essential tools for navigation and calendar making. Kepler published the Rudolphine Tables in 1627, using his laws to calculate planetary positions far more accurately than previous tables. These tables remained the standard reference for astronomers for over a century, demonstrating the practical value of theoretical accuracy. Modern space missions still use Keplerian orbital mechanics as the foundation for trajectory planning, modified only slightly by relativistic corrections. Part 3. Harmonices Mundi and the Music of the Spheres. Harmonices Mundi, published in 1619, represented Kepler's most ambitious attempt to unify geometry, music, astronomy and theology into one comprehensive system. The work spans 5 books covering geometric harmony, musical consonance, astrological aspects, planetary harmonies, and the relationship between celestial and psychological harmony. Kepler considered this his greatest achievement, surpassing even his planetary laws in philosophical significance. The central claim was that planetary motions embody musical harmonies detectable through mathematical analysis of their angular velocities at different orbital positions. The concept of cosmic harmony originated with Pythagoras, who discovered that musical intervals correspond to simple numerical ratios of string lengths. Dividing a string in half produces an octave with a ratio of 2 to 1. A ratio of 3 to 2 produces a fifth. Pythagoreans extended this discovery metaphorically, proposing that celestial bodies created cosmic music through their motions, though this music remained inaudible. Medieval philosophers taught this musica universalis as philosophical metaphor within the quadrivium of mathematical sciences. Kepler transformed this ancient metaphor into a literal mathematical claim based on actual planetary velocities rather than symbolic associations. He calculated the angular speeds of planets as observed from the Sun at their closest approach, called perihelion, and farthest distance called aphelion. These extreme velocities vary because planets move faster near the Sun and slower far from it, following the second law. The ratio between maximum and minimum angular speeds for each planet approximates specific musical intervals with remarkable accuracy. Saturn's extreme velocities vary in a ratio of approximately 4 to 5, corresponding to a major third in musical terminology. Jupiter's ratio approaches 5 to 6, a minor third. Mars achieves roughly 2 to 3, a perfect fifth. Earth varies by 15 to 16, the difference between the musical notes mi and fa, leading Kepler to declare that Earth sings mi fa mi, symbolizing misery and famine. Venus has nearly circular orbit, producing almost no variation, allowing only a single note. Mercury's highly elliptical path generates the widest harmonic range. These ratios were not exact, but approximated musical intervals within the measurement uncertainties and theoretical ambiguities of Kepler's calculations. Modern recalculations show discrepancies of several percent between Kepler's claimed harmonies and actual velocity ratios for some planets. The Mars-Jupiter velocity ratio fails to produce a consonant interval at all, creating an awkward gap in Kepler's harmonic scheme. He explained these imperfections by arguing that fitting elliptical orbits into the nested Platonic solids required slight deviations from ideal values. This willingness to excuse discrepancies reveals tensions in Kepler's methodology between empirical rigor and metaphysical commitment. For the planetary laws, he rejected 8 minutes of arc error as unacceptable. For cosmic harmonies, he tolerated larger deviations through theoretical adjustments. The difference reflects his certainty that laws describing actual motion must be exact, while harmonic relationships might allow flexibility for theological reasons. He was convinced that divine creation must embody harmony, making some harmonic pattern metaphysically necessary, even if details required interpretation. Kepler distinguished his celestial harmonies from Greek concepts by emphasizing that these were real but soundless mathematical relationships, not audible music. The harmonies existed objectively in the structure of motion itself, knowable through geometric and numerical analysis. They were perceived by the intellect, not the ear, representing abstract mathematical beauty rather than sensory experience. This intellectual perception aligned with his view that human rationality participated in divine rationality, allowing minds to grasp cosmic order. The harmonies also operated at multiple scales, creating polyphonic complexity when planetary velocities were compared across different planets simultaneously. Kepler imagined the planets forming a celestial choir with Saturn and Jupiter as bass voices, Mars as tenor, Earth and Venus as altos, and Mercury as soprano. At very rare intervals, perhaps only at creation, all planets might align in perfect harmonic concord, creating cosmic symphony. Most of the time, they produce more complex polyphonic relationships with occasional dissonances that resolve into consonances over longer timescales. This musical cosmology served multiple functions in Kepler's intellectual system beyond describing planetary motion aesthetically. First, it provided evidence for heliocentrism, because harmonic relationships only emerged when velocities were calculated from the Sun's perspective, not Earth's. Second, it offered teleological explanation for orbital eccentricities by showing that elliptical orbits were necessary for producing harmonic variety. Perfectly circular orbits would generate no velocity variation and thus no musical intervals, creating monotonous cosmic silence. Third, the harmonies explained why planetary orbits deviated slightly from the distances predicted by nested Platonic solids in Mysterium Cosmographicum. Geometry provided the rough structure, but musical harmony fine-tuned the exact distances to achieve optimal harmonic relationships. This hierarchical explanation subordinated geometry to harmony, reversing his earlier priority system. In one passage, Kepler explicitly states that geometric proportions must yield to harmonic beauty because harmony relates to motion, the soul and life of the system. This subordination reflects a deep metaphysical assumption that beauty and purpose take precedence over pure mathematical structure when they conflict. God created the cosmos not merely as a geometric demonstration, but as a beautiful, harmonious work, expressing divine creativity and rationality. The universe was meant to be contemplated with aesthetic appreciation, not just analyzed mathematically, engaging human emotional and intellectual faculties together. The harmonic framework also integrated astrology into Kepler's system. Though he rejected most traditional astrological claims as superstitious, he believed that particular angular relationships between planets, called aspects, affected terrestrial events through resonance with the human soul. The soul was naturally attuned to recognize harmonic ratios, responding unconsciously to planetary configurations that formed consonant or dissonant intervals. Astrological effects operated through psychological resonance with cosmic geometry rather than through causal influences or stellar emanations. This naturalized astrology by grounding it in geometry and musical theory while eliminating traditional mechanisms like planetary rays or astrological houses. Book 4 of Harmonices. Mundi explores how the human soul perceives harmony, arguing that souls respond to geometric and musical proportions because they share archetypal patterns with cosmic structure. God created human minds, structured to recognize the same harmonies embedded in celestial motions, allowing intellectual sympathy between microcosm and macrocosm. This explains why humans find certain musical intervals pleasant and others dissonant. We react to objective mathematical relationships that pervade creation. Kepler investigated musical theory extensively, refuting Pythagorean claims that all harmonies reduce to whole number ratios with a common unit. He demonstrated that no smallest interval or common factor exists from which all harmonies can be constructed through multiplication. Small discrepancies, called commas, accumulate when attempting to divide octaves into equal steps, requiring tempering systems to maintain harmonic relationships across keyboard instruments. This musical analysis displayed Kepler's rigorous mathematical approach to domains beyond astronomy, seeking exact relationships rather than accepting approximate rules. The discovery of the third law appeared in Book 5 of Harmonices Mundi as a culmination of the harmonic investigation. After describing how planetary velocity ratios form musical intervals, Kepler revealed the relationship between orbital periods and distances. This placement was not accidental. He viewed the period-distance relationship as the ultimate harmonic principle governing the entire solar system. The 3/2 power law connected the spatial dimension of orbits to their temporal dimension through a simple mathematical proportion, embodying cosmic unity. Kepler's harmonic cosmology influenced later thinkers in complex ways, sometimes generating admiration and sometimes skepticism. Enlightenment scholars dismissed the harmonic framework as mystical nonsense, focusing exclusively on the planetary laws as empirical discoveries. Romantic natural philosophers rehabilitated Kepler's vision, seeing him as a holistic thinker who integrated science, art, and spirituality. William Whewell, in his influential History of Science, portrayed Kepler as the archetype of inductive genius who combined mathematical rigor with aesthetic sensibility. Modern physics has occasionally rediscovered harmonic principles in unexpected contexts, though not in planetary orbits. Orbital resonances occur when celestial bodies' periods relate through simple integer ratios, creating stable or unstable gravitational interactions. Jupiter's moons Io, Europa, and Ganymede orbit in a 4:2:1 ratio, creating a genuine harmonic relationship through gravitational resonance. Some exoplanetary systems display similar resonances, showing that harmonic relationships can emerge from gravitational dynamics, though not universally as Kepler imagined. String theory in contemporary physics posits that fundamental particles are vibrations of tiny strings, with different vibrational modes producing different particles. This explicitly musical metaphor recalls Kepler's vision of cosmic harmony emerging from vibrational patterns, though the physical mechanisms are entirely different. The parallel suggests that seeking harmonic or vibrational explanations for natural phenomena remains an enduring intellectual strategy. However, Kepler's specific harmonic claims about planetary velocities failed empirically. The ratios are not precise enough to constitute genuine musical intervals. The whole framework depended on assuming that God designed the cosmos to embody musical beauty in specific ways. Without that theological assumption, there is no reason to expect planetary velocities would form consonant intervals at all. The appearance of approximate harmonies may reflect selection bias, where Kepler highlighted ratios that approximated musical intervals while explaining away those that did not. This raises questions about confirmation bias and motivated reasoning in scientific discovery. Did Kepler find what he wanted to find, rather than what was actually there? Yet his empirical rigour with the planetary laws demonstrates he could reject cherished ideas when evidence demanded it. The difference may be that he had independent observational evidence for the laws, but relied on theological assumptions for the harmonies. Where data clearly contradicted theory, he followed data. Where data was ambiguous, theological convictions guided interpretation. The musical cosmology also reveals assumptions about purposiveness in nature that modern science has largely abandoned, but that remain philosophically coherent. Kepler assumed the universe was designed with aesthetic intentions, making beauty a reliable guide to truth. Modern cosmology typically explains structure through mindless physical processes operating on initial conditions, producing order without purpose. But whether nature truly lacks purpose, or whether science simply excludes teleological questions from its methodology, remains philosophically contested. Some philosophers argue that excluding purpose from scientific explanation was methodologically productive, but not metaphysically necessary, allowing investigation of efficient causes without denying final causes. Kepler's combination of efficient causal explanations through solar force with final causal explanations through harmonic design represents an alternative framework still worth examining. Perhaps contemporary physics' difficulty unifying its fundamental theories reflects the loss of organizing principles that Kepler's harmonic approach once provided. Part 4. Theological and Metaphysical Foundations. Kepler's scientific work was inseparable from his Lutheran theological convictions about divine creation, intelligibility, and human purpose. He originally studied theology at the University of Tübingen, intending to become a Lutheran minister before his mathematical talents redirected him toward astronomy. This theological training profoundly shaped his scientific methodology, providing both motivation and conceptual framework for investigating cosmic structure. His fundamental premise was that God created the universe according to an intelligible mathematical plan accessible through natural reason, making science a form of divine revelation. The theological doctrine most central to Kepler's science was the belief that humans bear the image of God specifically through rationality. Because God is rational and humans possess God-given reason, human minds can comprehend the rational structure God embedded in creation. Geometry existed in the divine mind before the physical universe and was implanted in humans alongside the divine image. Therefore, discovering geometric patterns in nature was literally thinking God's thoughts after him, participating in divine knowledge. This optimism about human cognitive access to cosmic truth contrasted sharply with skeptical philosophies doubting whether human faculties reliably grasp reality. Kepler's confidence that mathematical reasoning reveals actual structure rather than merely constructing useful fictions enabled his realist interpretation of heliocentrism. If human reason genuinely participates in divine reason, then careful mathematical analysis should uncover how creation actually is, not merely how it appears. Lutheran theology emphasized that general revelation through nature complements special revelation through Scripture, providing two books through which God communicates truth. Kepler viewed his astronomical work as reading the book of nature, deciphering the mathematical language in which God wrote the physical world. This justified scientific investigation as religious vocation, making the study of nature a form of worship, honoring the Creator. In several letters, Kepler expressed that his astronomical discoveries praised God as effectively as any theological work could. He wrote that he had wanted to become a theologian, but now God was glorified through his astronomy instead, fulfilling his religious calling through scientific investigation. This fusion of scientific and religious purpose resolved the apparent conflict between his theological training and astronomical career. Rather than abandoning religion for science, he pursued science as religion, treating empirical investigation as theological exploration. The sun occupied special theological significance in Kepler's cosmology as a symbol and perhaps even an image of God the Father. He proposed a Trinitarian cosmology where the sun represented God the Father, the stellar sphere represented God the Son, and the space between represented the Holy Spirit. This was not merely poetic symbolism, but a claim about cosmic structure mirroring divine nature. The sun's centrality in the heliocentric system thus had theological justification beyond empirical evidence or mathematical convenience. Kepler believed the sun actively governed planetary motion through a force emanating from its rotating body, similar to how God governs creation. Earlier, Copernican advocates treated the sun as passive, with planets somehow naturally orbiting it without requiring causal explanation. Kepler insisted that motion requires an active moving force, which could only originate from the sun as the dynamic center of the system. This physical intuition was partly driven by theological conviction that the sun, representing divine power, must be causally active rather than inert. His view of the sun as divine image also influenced his rejection of geocentrism on theological grounds beyond empirical considerations. Placing Earth at the center implied that humanity and terrestrial affairs occupied the cosmically privileged position, which Kepler found theologically presumptuous. The sun, being more excellent and representing God, deserved the central position as the true source of light, heat and motion. This argument reversed traditional geocentric logic, which had placed Earth centrally because it was heavy and base, not excellent and divine. Kepler's natural theology also addressed the question of why God created precisely this cosmos rather than some other possible arrangement. He rejected the view that creation was arbitrary or contingent on divine whim, arguing instead that God's rationality constrained creative choices. The use of Platonic solids to structure planetary distances represented necessary choices, not arbitrary decisions, because only 5 such solids exist mathematically. Similarly, harmonic relationships emerged from the geometric and mathematical archetypes co-eternal with God's mind, making the actual cosmos the uniquely rational creation. This raised subtle theological issues about divine freedom versus divine rationality that had troubled Christian theology since Augustine. If God's creative choices were constrained by mathematical necessity, did that limit divine omnipotence or freedom? Kepler navigated this by identifying God's reason with God's essence, making rational constraints internal to divine nature rather than external limitations. God freely created according to reason because God is reason itself, so rational necessity and divine freedom coincide rather than conflict. The geometric archetypes that structured creation existed in God's mind eternally, not as separate forms but as aspects of divine thought. When God created the physical universe, these archetypal patterns became instantiated in matter, making material reality a reflection of divine intellect. This Platonic metaphysics positioned mathematics as the mediating realm between divine mind and physical world, explaining why mathematical analysis reveals cosmic structure. Kepler carefully distinguished his views from ancient paganism that had divinized celestial bodies themselves or attributed souls to planets. He explicitly rejected Aristotelian animism that treated planets as living beings moving through internal vital principles. Instead, he proposed mechanical causation through solar force, comparing planetary motion to a clock mechanism driven by a simple weight. Giving a clock a soul, he wrote, dishonors the clockmaker by attributing to the machine what belongs to its creator. This mechanical analogy represented an important shift toward modern mechanistic philosophy while retaining theological purpose. The universe operated through regular law-governed mechanisms that humans could understand mathematically without requiring mysterious vital forces or divine intervention at every moment. God designed and created the cosmic mechanism, but then governed it through stable natural laws rather than constant supernatural action. This preserved both divine transcendence through the initial creative act and divine immanence through the rational laws pervading nature. However, Kepler's mechanism was not purely materialistic because he believed the sun's rotating body generated the force moving planets through a quasi-magnetic spiritual power. This force was immaterial, though physical, operating through space without requiring material contact or medium. The concept anticipated action at a distance that later troubled Newtonian mechanics, but was theologically acceptable because spirit could act where body could not. Kepler also addressed potential conflicts between his astronomy and biblical passages that seemed to support geocentrism or describe the sun's motion. Joshua's command for the sun to stand still and Ecclesiastes' statement that the sun rises and sets appeared to contradict heliocentrism. He argued that Scripture accommodates common perceptual experience when discussing natural phenomena, using phenomenological language rather than making technical astronomical claims. The Bible aims to communicate spiritual truth, not to teach astronomy. So apparent geocentric references are figures of speech adapted to human perspective. This hermeneutical principle allowed Kepler to maintain both biblical authority and heliocentrism without conflict by distinguishing scriptural purposes from scientific claims. The principle itself was not novel. Augustine had articulated similar ideas about scriptural accommodation centuries earlier. But Kepler applied it systematically to defend Copernicanism theologically, providing intellectual resources for Protestants who might otherwise reject heliocentrism as unbiblical. His theological heterodoxy on certain Lutheran doctrinal points created practical difficulties throughout his life, despite his genuine piety. He questioned aspects of the Formula of Concord, the Lutheran confessional statement, and advocated for communion fellowship across Protestant denominations. These positions got him excluded from Lutheran communion and blocked his appointment to academic positions at Lutheran universities. Yet his theological independence reflected the same commitment to truth over convention that drove his scientific work. He would not affirm doctrines he found incoherent merely for institutional acceptance, applying intellectual honesty to theology as rigorously as to astronomy. The relationship between Kepler's theology and science raises broader questions about whether religious commitments help or hinder scientific investigation. Standard secularization narratives portray science as progressively liberating itself from religious constraints to achieve objectivity. But Kepler's case demonstrates that specific theological convictions actively enabled revolutionary scientific discoveries by providing motivation, conceptual resources, and metaphysical frameworks. Without his conviction that creation was rationally ordered, he might have settled for approximate circular models like his predecessors. His certainty that God structured the cosmos geometrically drove him to seek exact mathematical relationships that others dismissed as unattainable. The confidence that human reason could comprehend divine design prevented premature skepticism about whether precise laws governing nature even existed. And his theological conviction that nothing in creation was arbitrary motivated the search for necessary explanations when others accepted contingent descriptions. This suggests that the relationship between religion and science is more complex than simple conflict or independence models acknowledge. Certain theological frameworks may be more conducive to scientific investigation than others, particularly those emphasizing creation's rational order and human cognitive access to truth. Kepler's Lutheran convictions about natural revelation and the divine image in human rationality created an intellectual environment where scientific investigation became religiously meaningful. However, the same theological convictions that enabled his discoveries also introduced biases, as seen in his willingness to overlook discrepancies in cosmic harmonies. Religious commitment to finding divine harmony occasionally overwhelmed empirical rigor, leading him to see patterns where only approximations existed. The productive tension was that his theology both motivated relentless pursuit of truth and occasionally predetermined what truths he expected to find. Contemporary philosophy of science largely excludes theological considerations from scientific methodology, treating them as historically interesting but epistemically irrelevant. Yet Kepler's integration of theology and science raises the question whether this exclusion eliminates potentially productive metaphysical frameworks. If belief in cosmic rationality and order motivates scientific investigation, might abandoning such beliefs undermine the very confidence that nature is comprehensible through reason? Some philosophers argue that science depends on metaphysical assumptions about nature's regularity and intelligibility that lack empirical justification without theological grounding. Others respond that science has successfully naturalized these assumptions, treating them as methodological principles rather than metaphysical claims requiring theological support. Nature appears regular enough for scientific investigation, regardless of whether divinity designed that regularity or it emerged through mindless processes. The debate continues about whether modern science's exclusion of purpose and design from explanatory frameworks represents genuine metaphysical insight or merely methodological restriction. Part 5. Physical Causation and the Solar Force. Kepler revolutionized astronomy by insisting that describing planetary motion required physical explanations for why planets move, not just geometric models of how they appear to move. Ancient and medieval astronomy had treated planetary positions as a purely mathematical problem, solvable through geometric constructions without addressing physical causes. Aristotelian natural philosophy discussed physical cosmology separately from mathematical astronomy, creating a disciplinary divide between calculating positions and explaining motion. Kepler deliberately crossed this boundary, transforming astronomy into what he called celestial physics by demanding causal mechanisms for observed motions. His central physical insight was that some force emanating from the Sun must actively drive planetary motion rather than planets moving naturally through inner principles. This contradicted Aristotelian physics, where celestial bodies moved eternally through their own nature without requiring external movers beyond the prime mover. It also departed from Copernican astronomy, which merely rearranged the geometric system without addressing what caused planets to orbit the Sun. Kepler argued that motion requires a continuous mover, and only the Sun possessed the physical properties necessary to move 6 planets simultaneously across vast distances. He hypothesized that the Sun rotates on its axis and emits species or fibers that sweep through space like rotating spokes on a wheel. These solar fibers contact planets and push them along their orbital paths, with the force weakening as distance from the Sun increases. The longer the fiber, the weaker its pushing power, explaining why outer planets move more slowly than inner ones. This mechanism connected orbital speed directly to solar distance through a physical process rather than through arbitrary mathematical rules. Kepler's solar force theory drew inspiration from William Gilbert's work on magnetism, published in 1600 as De Magnete. Gilbert demonstrated that Earth itself was a giant magnet, making magnetism a cosmic force rather than merely a mineral property. Kepler adapted magnetic concepts, proposing that the Sun possessed magnetic properties that affected planetary motion through attraction and repulsion. He suggested that planets had magnetic poles that interacted with solar magnetism, alternately approaching and receding from the Sun as they orbited. This quasi-magnetic force theory was empirically incorrect in its details, but conceptually revolutionary in several respects. First, it introduced the idea of action at a distance, where one body affects another across empty space without material contact. Aristotelian physics had required direct contact for causal influence, making celestial motion through vacuum spaces philosophically problematic. Magnetism demonstrated that forces could operate through space, providing a physical model for how the Sun might move distant planets. Second, it made force strength dependent on distance in a way that could be quantified mathematically, anticipating the inverse square law of gravitation. Kepler initially proposed that solar force weakened inversely with distance, meaning twice the distance produced half the force. This linear relationship was incorrect. Gravitational force actually weakens as the inverse square of distance. But the conceptual move of making force a mathematical function of distance represented crucial progress toward Newtonian mechanics. Third, it unified celestial and terrestrial physics by applying the same kind of force to both domains, breaking down the ancient division between sublunary and superlunary realms. If magnetism operated both on Earth and in the heavens, then perhaps all physical forces worked universally rather than being realm-specific. This universalization of physics became central to the scientific revolution, culminating in Newton's universal gravitation applying identically everywhere. Kepler's distance law for orbital speed stated that velocity is inversely proportional to distance from the Sun, which worked approximately for nearly circular orbits. But he discovered this only held exactly for circular motion, failing for the elliptical orbits he had proven planets actually follow. The distance law predicted that a planet's orbital period would be proportional to the area of its orbit because slower speeds at greater distances would exactly compensate for longer path lengths. However, calculations showed this prediction was incorrect, forcing Kepler to revise his physical theory. He refined the distance law into the area law, stating that the line from Sun to planet sweeps equal areas in equal times, rather than moving at speeds inversely proportional to distance. This area law held exactly for all elliptical orbits, regardless of eccentricity, making it more fundamental than the distance law. The area law implicitly contained what modern physics calls conservation of angular momentum, though Kepler lacked that conceptual framework entirely. He derived it through geometric reasoning about how radial distances and arc lengths must relate to maintain equal triangular areas over equal times. The physical mechanism Kepler proposed to explain the area law involved both the tangential solar force pushing planets along their orbits and radial magnetic forces alternately attracting and repelling them toward or away from the Sun. As planets approached the Sun, magnetic repulsion would slow their radial infall, while tangential force accelerated their orbital motion. As they receded, magnetic attraction would slow their radial escape, while weaker tangential force decelerated their orbit. This combination of forces would produce elliptical motion with varying speed, though Kepler never developed the mathematics to derive ellipses rigorously from these forces. His physical theory faced several conceptual difficulties that Kepler acknowledged but could not resolve with the physics available to him. The most serious problem was explaining how the Sun could continuously emit force to move planets without being depleted or exhausted over time. If the Sun lost energy by pushing planets, it should gradually weaken and planetary motion should decay, which observations did not support. Kepler had no concept of force conservation or the principle that gravitational force does not require energy expenditure. So this remained a persistent puzzle. Another difficulty involved explaining why some planets have more elliptical orbits than others if all are driven by the same solar force mechanism. Mars has much higher eccentricity than Venus, despite both being subject to identical solar fibers pushing them. Kepler attributed these differences to intrinsic magnetic properties of different planets, with Mars having stronger magnetic poles than Venus. But this explanation was ad hoc, introducing arbitrary planetary properties to account for orbital differences without independent evidence. The relationship between Kepler's physical theories and his mathematical laws reveals an important epistemological pattern in the history of science. His physical explanations were largely wrong in their specifics. There are no solar fibers pushing planets along, and magnetism does not govern orbital motion. Yet his mathematical descriptions of orbital motion were exactly correct and remain valid today with only minor relativistic corrections. This divergence between successful mathematics and failed physics raises questions about whether correct equations require correct physical understanding. Modern philosophy of science distinguishes between phenomenological laws that describe observable patterns and theoretical explanations that identify underlying mechanisms. Kepler's three laws function as phenomenological descriptions that accurately capture orbital behavior regardless of which forces produce that behavior. His solar force theory represented an attempt at theoretical explanation that failed because he lacked the conceptual resources to identify gravitational attraction as the actual mechanism. The laws survived while the mechanism was replaced, demonstrating that descriptive accuracy can outlast explanatory frameworks. However, Kepler's physical intuitions, though technically wrong, were conceptually productive in ways that enabled later progress. His insistence that some force from the Sun moves planets established the agenda for Newton's gravitational theory 7 decades later. His proposal that force weakens with distance anticipated the inverse square law, even though he got the precise mathematical relationship wrong. And his conviction that celestial motion required physical causation helped transform astronomy from descriptive geometry into dynamical physics. Isaac Newton explicitly built on Kepler's work, but also had to overcome some of Kepler's physical assumptions to arrive at universal gravitation. Kepler's solar force theory was unidirectional, flowing from Sun to planets without reciprocal forces from planets back to the Sun. Newton's third law of action and reaction required that gravitational force operates mutually, with planets attracting the Sun just as much as the Sun attracts planets. This mutuality meant the Sun itself must orbit the system's centre of mass rather than remaining perfectly stationary, as Kepler had assumed. Kepler also believed that force required some kind of material or quasi-material substance to transmit influence, whether fibers or magnetic emanations. Newton's gravitational force acted instantaneously across empty space without any mediating substance, which Newton himself found philosophically troubling. He admitted that action at a distance through vacuum seemed absurd, but insisted the mathematics demanded it regardless of philosophical plausibility. This willingness to accept mathematically necessary but conceptually mysterious forces represented another break from Aristotelian requirements for physical intelligibility. The development from Kepler's solar force to Newton's universal gravitation illustrates how scientific progress often involves both continuity and radical reconceptualization. Kepler established the problem space by showing that orbital motion requires force, and that force must vary with distance mathematically. Newton solved that problem by identifying the specific force and its mathematical form, but doing so required abandoning many of Kepler's specific assumptions. Progress was neither purely cumulative addition of new facts nor complete revolutionary replacement of frameworks, but a complex mixture of both. Kepler's physical reasoning also reveals assumptions about causation and explanation that have since evolved in physics. He assumed that explaining motion meant identifying what actively pushes or pulls things, requiring a positive causal agent producing change. Modern physics sometimes treats forces as derivative concepts explained through more fundamental principles like field equations or symmetry conservation. General relativity eliminates gravitational force entirely, replacing it with space-time curvature where objects follow geodesics without any force acting. This progression raises philosophical questions about whether physics explains the same phenomena more deeply across theoretical changes, or whether different theories address fundamentally different questions. Does general relativity explain gravity better than Newton, or does it reconceive what needs explaining by eliminating force in favour of geometry? Kepler's solar force, Newton's gravitational attraction, and Einstein's spacetime curvature might be three different ways of conceptualizing orbital motion that cannot be straightforwardly ranked as progressive improvements. The influence of Kepler's physical thinking extended beyond astronomy into the development of mechanistic natural philosophy during the 17th century. Descartes, Gassendi, and others pursued mechanical explanations for natural phenomena by identifying particles, collisions, and pushes as fundamental causal mechanisms. Kepler's analogy of the cosmos as a clockwork mechanism driven by simple forces anticipated this mechanical philosophy while retaining some Aristotelian concepts. His work represented a transitional stage between Aristotelian natural philosophy and fully mechanistic physics, incorporating elements of both without completely belonging to either. Part 6. Optics and the Theory of Light. Kepler's contributions to optics were as revolutionary as his astronomical discoveries, fundamentally transforming understanding of vision, light, and image formation. His major optical work, Astronomiae Pars Optica, published in 1604, established the mathematical foundations of modern optics decades before his astronomical laws gained acceptance. He explained how lenses form images, derived the law of refraction approximately, analyzed camera obscura, and developed the first correct theory of vision. These achievements made him the father of modern optics alongside his role in astronomy, demonstrating intellectual breadth rare even among great scientists. The problem that initially drove Kepler's optical research was astronomical, understanding how the eye perceives celestial objects and how atmospheric refraction affects observations. Previous astronomers had noticed that stars appeared higher above the horizon than their true positions because Earth's atmosphere bends incoming light rays. But without understanding refraction precisely, they could not calculate corrections accurately, introducing errors into observational data. Kepler needed optical theory to interpret Tycho's observations correctly and to understand how telescopes worked after Galileo's discoveries in 1609. Medieval optical theory, following ancient sources like Euclid and Ptolemy, treated vision as rays emanating from the eye toward objects rather than light entering the eye from objects. This extramission theory made eyes active emitters rather than passive receivers, which seemed to explain how vision was directed towards specific objects intentionally. Kepler overturned this entirely, demonstrating that vision results from light rays travelling from objects into the eye where they form images on the retina. This intromission theory required explaining how external rays produce internal images and how those retinal images relate to conscious visual perception. Kepler's crucial insight was that the eye functions like a camera obscura, forming inverted images on the retina through refraction in the crystalline lens. He performed anatomical dissections and geometric analysis to trace how light rays converge after passing through the cornea and lens. Each point on an external object emits rays in all directions. The lens refracts these rays to converge at corresponding points on the retina, creating an inverted, reversed image. This explained how a continuous picture of the external scene could appear on the retina, despite being smaller, inverted, and physically distinct from the viewed objects. The inversion of the retinal image created a philosophical problem. If we see an upside-down image, why do we perceive the world right side up? Kepler's solution was that vision involves not just physical image formation, but mental processing that interprets retinal patterns. The mind judges spatial relationships based on experience and reasoning, not by directly viewing the retinal image as if with an inner eye. This separated the physical optics of image formation from the psychological aspects of visual perception, establishing a mind-body distinction within vision theory. He wrote that his optical theory explained everything up to the retinal image, but how that image becomes conscious perception belonged to philosophers and physicians to explain. This methodological move created a boundary between physical and mental sciences that remains influential in contemporary cognitive science. The hard problem of consciousness, explaining how physical processes produce subjective experience, has roots in Kepler's recognition that optical physics cannot fully explain vision. Kepler also investigated refraction, seeking mathematical laws governing how light bends when passing between different transparent media like air, water, or glass. He discovered empirically that the ratio of signs of incident and refracted angles remained approximately constant for small angles, approaching what we now call Snell's law. However, he lacked the mathematical tools to formulate the exact law rigorously and did not achieve Willibord Snell's later precise formulation. Nevertheless, his approximations were accurate enough for most practical optical calculations, including lens design and atmospheric refraction corrections. His work on refraction enabled him to calculate how Earth's atmosphere bends starlight, showing that atmospheric refraction increases as objects approach the horizon. He developed tables allowing astronomers to correct observed positions for atmospheric effects, significantly improving observational accuracy. These corrections were essential for his own planetary calculations based on Tycho's data, since without them systematic errors would have undermined his laws. Thus, Kepler's optics directly enabled his astronomy by providing the theoretical foundations for interpreting observations correctly. Kepler also studied the intensity of light, proposing that brightness diminishes with the inverse square of distance from a point source. If you double the distance from a candle, its light spreads over 4 times the area, reducing intensity to 1/4. This geometric reasoning about light spreading through space in straight lines established the inverse square law for electromagnetic radiation long before understanding its physical nature. The parallel between his inverse distance law for solar force and inverse square law for light intensity suggests he recognized similarities between different spatial influences, though he never unified them. His optical work also addressed the nature of light itself, though he could not resolve whether light was substance, quality, or process. Medieval Aristotelian physics treated light as a quality inhering in transparent media rather than a substance existing independently. Kepler rejected substantial theories of light while acknowledging that light travelled through space with finite speed, though so fast that astronomical distances did not produce noticeable delays. He lacked the conceptual framework to decide between wave and particle theories of light, an issue that persisted for centuries until quantum mechanics showed light exhibits both properties. Kepler's investigation of lenses and telescopes became urgent after Galileo announced telescopic discoveries of Jupiter's moons and lunar mountains in 1610. Kepler quickly wrote Dioptris, published in 1611, analysing how combinations of lenses magnify and focus light. He explained the principles behind both Galilean telescopes using concave eyepieces and his own design using convex lenses, which inverted the image but provided wider fields of view. This theoretical grounding transformed telescopes from empirical instruments into scientifically understood tools whose behaviour could be predicted and optimized. His optical theories also intersected with his metaphysics in interesting ways, particularly regarding the relationship between light and the divine. Light occupied special theological and philosophical status in medieval and Renaissance thought as the most noble and spiritual of physical phenomena. Kepler saw light as fundamentally different from matter, being incorporeal yet physically real, making it an appropriate symbol for divine presence in creation. The sun's emission of light connected to his theology of the sun as God's image, radiating influence throughout the cosmos analogously to divine providence. However, Kepler's treatment of light was more mathematical and mechanical than his predecessors, focusing on geometric ray tracing rather than metaphysical speculations about light's essence. This represented another aspect of his broader project of mathematizing natural philosophy, treating even spiritually significant phenomena as subject to quantitative analysis. Light could remain theologically meaningful while being studied through geometry and experiment, demonstrating how Kepler integrated religious meaning with scientific method. The relationship between Kepler's optics and his astronomy also illustrates how technological developments drive theoretical innovation in science. The invention of the telescope created both opportunities for new observations and challenges for interpreting those observations. Without optical theory explaining how telescopes work, their discoveries could be dismissed as instrumental artifacts rather than genuine observations of celestial reality. Kepler's optical work provided the theoretical credibility necessary for accepting telescopic observations as reliable evidence about the heavens. His emphasis on the eye as a passive receiver of light rather than active emitter also had epistemological implications for how observation relates to reality. If vision resulted from light coming from objects into eyes, then what we see depends on actual properties of external things, rather than projections from our minds. This supported realist interpretations of observational evidence, undercutting skeptical arguments that appearances might be purely subjective constructions. The mechanistic account of image formation on the retina provided physical grounds for trusting that vision reveals real features of the external world. Kepler's optical work influenced numerous later scientists, including Descartes, who developed mathematical theory of refraction, and Newton, who investigated light's composition and colour. The camera obscura model of the eye remained standard until the 19th century, when Hermann von Helmholtz refined it further. Modern understanding of vision still incorporates Kepler's basic insights about image formation through refraction, supplemented by knowledge of photoreceptors and neural processing he could not have possessed. His achievements in optics demonstrate that great scientific contributions often involve synthesizing insights from multiple domains rather than revolutionary breakthroughs in isolation. Kepler combined geometrical analysis, anatomical knowledge, experimental observation, and philosophical reflection to construct his optical theory. No single insight explains his success. Rather, his ability to integrate mathematical, empirical, and conceptual resources enabled systematic progress where others had fragmented understanding. This interdisciplinary integration characterized all his best work, from astronomy through optics to mathematical physics. Part 7. The Living Cosmos and Astrology. Kepler's relationship with astrology was complex and ambivalent, simultaneously defending and reforming it while rejecting most traditional astrological claims. He earned substantial income as an imperial mathematician by casting horoscopes for Emperor Rudolf II and other nobility. Yet he privately scorned the superstitious elements of popular astrology, calling it the foolish daughter who must support her wise mother astronomy financially. This tension between intellectual skepticism and practical necessity forced him to develop a reformed naturalistic astrology grounded in geometry rather than tradition. Traditional astrology divided the zodiac into 12 houses, assigned planetary rulerships, and interpreted conjunctions through elaborate symbolic systems inherited from Hellenistic and Arabic sources. Kepler rejected most of this apparatus as arbitrary convention, lacking rational foundation, dismissing concepts like planetary exaltations and astrological houses. He argued that if astrological influences were real, they must operate through natural mechanisms, discoverable through reason, not through occult sympathies or ancient authorities. His reformed astrology retained only those elements that could be explained geometrically through angular relationships between planets, called aspects. Aspects occur when planets form specific angular separations in the sky. Conjunction at 0 degrees, opposition at 180 degrees, trine at 120 degrees, and so forth. Kepler proposed that these aspects influence terrestrial events not through planetary emanations or stellar rays, but through resonance with the human soul. The soul possessed innate sensitivity to geometric harmonies, responding unconsciously when planetary positions formed consonant or dissonant angular intervals. This psychological mechanism naturalized astrology by grounding it in the same harmonic principles governing music and cosmic structure. He developed a doctrine of the anima terrae, the soul of the earth, which he believed possessed sensitivity to celestial configurations. This terrestrial soul was not a conscious mind, but an animating principle that responded to geometric patterns in planetary positions, influencing weather and geological phenomena. When planets formed harmonic aspects, the Earth's soul resonated sympathetically, producing meteorological effects like storms or calm weather. Similarly, human souls contained geometric archetypes that resonated with celestial harmonies, explaining astrological influences on personality and fortune. This theory required the bold assumption that souls possessed mathematical structure and responded to abstract geometric relationships automatically without conscious awareness. Kepler drew on Platonic psychology, which posited that souls contained innate mathematical knowledge and geometric archetypes from before birth. These innate patterns allowed souls to recognize harmonic proportions in music, visual art, and celestial configurations, producing emotional and physiological responses. Astrological effects thus operated through psychological resonance rather than physical causation, making them real but not mechanically deterministic. Kepler explicitly rejected astrological determinism, arguing that celestial influences inclined but did not compel human actions or fate. The soul's response to planetary aspects could be modified by reason, virtue, and free will, preventing strict causal determination. This preserved moral responsibility while allowing for astrological influences, navigating between complete determinism and pure chance. His position reflected Lutheran theology's emphasis on human freedom despite divine providence, transposed into the relationship between celestial influences and human agency. He also criticized astrologers for claiming to predict specific events with certainty, arguing that astrology could at best indicate general tendencies and probabilities. The soul's response to aspects was variable, depending on individual temperament, circumstances, and choices, making precise predictions impossible. Astrologers succeeded occasionally through lucky guesses or vague statements fitting many situations, not through genuine predictive science. Kepler's own horoscopes were often deliberately ambiguous, acknowledging astrology's limitations while satisfying patrons' expectations for astrological counsel. His defense of reformed astrology rested partly on empirical claims about correlations between celestial configurations and terrestrial events. He observed that certain weather patterns seemed associated with particular planetary aspects, though he acknowledged that correlations were statistical rather than absolute. Modern meteorology finds no evidence for such correlations. Atmospheric phenomena depend on local physical conditions, not planetary positions. Kepler's observations likely reflected confirmation bias, where memorable coincidences between aspects and weather reinforced belief, while contrary instances were forgotten. The concept of a living cosmos with a terrestrial soul marked Kepler as transitional between ancient animism and modern mechanism. Aristotelian cosmology had treated celestial bodies as living beings, with souls driving their eternal motions through internal, vital principles. The mechanistic philosophy emerging in the 17th century would eliminate souls entirely, explaining all phenomena through matter in motion governed by impersonal laws. Kepler occupied an intermediate position, mechanizing celestial motion through solar force while retaining Earth's soul as the principle of astrological sensitivity and geological activity. This hybrid approach allowed him to reject Aristotelian animism for the heavens while preserving vital principles for Earth, creating an asymmetric cosmology. Planets moved mechanically like clockwork, yet Earth retained a soul capable of geometric perception and response. The inconsistency reveals tensions in his thought between emerging mechanistic physics and traditional vitalism that he never fully resolved. Later thinkers would eliminate Earth's soul along with celestial souls, completing the mechanization of nature that Kepler only partially accomplished. Kepler's astrological writings also reveal how he navigated between intellectual conviction and economic necessity in ways that raise questions about scientific integrity. He privately expressed skepticism about astrology's predictive value while publicly offering astrological services to patrons who paid for horoscopes. This apparent hypocrisy might be condemned as intellectual dishonesty, but Kepler himself acknowledged the tension explicitly, defending astrology as a legitimate if limited field. He genuinely believed that planetary aspects influence terrestrial events through harmonic resonance, even while rejecting most traditional astrological doctrines. The relationship between Kepler's astrology and his astronomy also illustrates how the same geometric and harmonic principles unified his diverse intellectual projects. Astrological aspects were based on divisions of the circle into segments related by harmonic ratios, exactly paralleling his cosmic harmonies. A trine aspect, dividing the zodiac into thirds, corresponded to musical intervals, dividing octaves into consonant proportions. This conceptual unity meant that rejecting astrology entirely would undermine the harmonic cosmology that Kepler believed revealed divine design. His defense of astrology, therefore, was not merely mercenary, but integrated with his broader metaphysical system about cosmic harmony and geometric causation. If planetary velocities embodied musical harmonies and geometries structured the cosmos, then geometric configurations should produce real effects through harmonic resonance. Astrology became an extension of his harmonic philosophy applied to terrestrial phenomena rather than an isolated superstition. From this perspective, his astrology was as principled as his astronomy, even if empirically mistaken. Modern historians of science disagree about whether to view Kepler's astrology sympathetically as part of his unified natural philosophy or to dismiss it as embarrassing superstition. Some emphasize that astrology was intellectually respectable in the 17th century, practiced by many learned people without stigma. Condemning Kepler for astrological beliefs imposes anachronistic standards from contemporary science onto a very different intellectual context. Others argue that even by 17th century standards, Kepler's defense of astrology was weak, and his skeptical contemporaries recognize its lack of empirical support. The case raises broader methodological questions about how historians should evaluate past scientific beliefs now known to be false. Should we credit scientists only for discoveries that match current knowledge or appreciate their entire intellectual systems within historical context? Kepler's astrology was logically connected to his cosmology in ways that made rejecting one while accepting the other difficult without modern knowledge distinguishing them. Judging his astrology harshly while celebrating his astronomy may reflect hindsight bias rather than fair historical assessment. The doctrine of the anima terrae also connects to contemporary Gaia theory, which treats Earth as a self-regulating system exhibiting properties analogous to living organisms. James Lovelock's proposal that Earth's biosphere maintains homeostatic conditions for life has been criticized as neo-vitalism, reviving discredited animistic concepts. Yet some biologists defend Gaia theory as legitimate systems biology studying feedback mechanisms without requiring literal organismic interpretation. The parallel with Kepler's terrestrial soul suggests that debates about whether Earth constitutes a living system have deep historical roots in varying concepts of life and organization. Kepler's astrological work declined in influence more rapidly than his astronomical discoveries because astrology could not be integrated into mechanistic natural philosophy. Newton's physics explained planetary motion through universal gravitation, without requiring harmonic proportions or geometric resonances affecting Earth or souls. Astrology became intellectually marginal during the Enlightenment as mechanism displaced vitalism, and empirical testing revealed no reliable correlations between celestial and terrestrial events. By the 19th century, astrology survived only as popular superstition divorced from serious science, reversing the 17th century situation where it was respectable scholarly practice. Yet Kepler's attempt to reform astrology on rational principles illustrates an important pattern in scientific development, trying to preserve traditional practices by reformulating them within new frameworks. Rather than simply rejecting astrology entirely, he sought to identify which elements could be justified scientifically and which were superstitious accretions. This reformist approach sometimes succeeds in preserving modified versions of traditional knowledge within modern science, as with herbal medicine becoming pharmacology. In astrology's case, the reform failed because the core causal claims were false, regardless of theoretical reformulation. The broader lesson is that not all traditional knowledge can be successfully reformed and integrated into scientific frameworks, but distinguishing salvageable from unsalvageable elements often requires attempting the integration. Kepler's astrological project failed instructively, demonstrating through rigorous effort that astrology could not be naturalized within geometric physics. Part 8. Scientific Method and Epistemology. Kepler's scientific methodology combined mathematical rigor, empirical precision, creative hypothesis formation, and systematic error analysis in ways that established new standards for astronomical research. His approach was neither purely empiricist, deriving laws from observations alone, nor purely rationalist, deducing truths from mathematical principles without observational constraint. Instead, he practiced what philosophers now call hypothetico-deductive method, proposing theoretical models and testing them against data through increasingly rigorous comparison. This dialectical interplay between theory and observation became paradigmatic for modern science, though Kepler himself never articulated it as explicit methodological doctrine. His treatment of observational error was revolutionary, recognizing that measurements contained uncertainties requiring careful analysis rather than simple dismissal. Medieval astronomy had distinguished true positions from observed positions, but treated discrepancies as corruptions to be corrected rather than as systematic data about measurement precision. Kepler instead analyzed error patterns to extract information about both measurement limitations and real phenomena being measured. When his models disagreed with observations, he considered whether the observations might be wrong, the theory might be wrong, or both might contain different kinds of errors. The famous 8-minute discrepancy in Mars's position exemplified this sophisticated error analysis, where he distinguished measurement error from theoretical inadequacy. Tycho's observations were accurate to approximately 2 minutes under good conditions, meaning 8-minute systematic discrepancies exceeded reasonable measurement error. Rather than dismissing the discrepancy or adjusting data to fit theory, Kepler concluded that his circular orbit model was fundamentally wrong. This decision established the principle that persistent systematic errors indicate theoretical failure rather than observational incompatibility. A crucial insight for scientific methodology. Kepler's use of multiple working hypotheses also demonstrated methodological sophistication, testing various theoretical alternatives against the same observational data. For Mars' orbit, he tried bisecting the eccentricity, introducing additional epicycles, adjusting equant points and various oval shapes before discovering ellipses. Each failed hypothesis provided information about what constraints any successful theory must satisfy, progressively narrowing the solution space. This process of elimination through systematic hypothesis testing contrasted with medieval approaches that defended established models by adding complexity rather than reconsidering foundations. He also pioneered the method of thought experiments, imagining how observers at different locations would perceive planetary motions to test theoretical claims. In Astronomia Nova, he imagined viewing planets from the Sun rather than Earth, reasoning that physical causes should operate from the Sun's perspective in a heliocentric system. This shift in reference frame allowed him to discover relationships between solar distance and orbital speed that were obscured from Earth's viewpoint. The technique anticipated Einstein's use of thought experiments involving imaginary observers in accelerating frames or travelling at light speed to derive relativistic principles. Kepler's methodology also involved extensive calculation and numerical analysis on scales unprecedented for his era, filling thousands of manuscript pages with arithmetic. Before electronic computers, such calculations required immense labour, patience, and organisational skill to manage without accumulating fatal errors. He developed systematic procedures for checking calculations, often repeating them multiple ways to verify results, establishing quality control practices still essential in computational science. The sheer volume of calculation demonstrated his commitment to empirical precision, refusing to settle for qualitative agreement when quantitative accuracy was achievable. His reasoning about physical causes also displayed methodological awareness about different types of explanation and their appropriate domains. He distinguished between mathematical descriptions that captured patterns without explaining causes and physical theories that identified mechanisms producing observed behaviors. Mathematical models could be useful even if physically false, as Ptolemaic astronomy was computationally effective despite geocentric errors. But Kepler insisted that ultimately science should seek physical truth, not just predictive accuracy, making realism about theoretical entities essential to his epistemology. This realist stance created tension with instrumentalist contemporaries who viewed all astronomical models as mere calculating devices without physical significance. Kepler argued that if two models made different predictions, observations could determine which was physically true rather than merely more convenient. His confidence that empirical evidence could adjudicate between competing theories required believing that observations revealed objective reality rather than being theory-laden constructions. This epistemological optimism about observational access to truth distinguished him from skeptics, doubting whether human knowledge transcended appearances. Kepler also recognized the role of aesthetic considerations in theory choice, though he struggled with how to balance beauty against empirical adequacy. He initially preferred circular orbits because circles seem perfect and divinely appropriate, showing that aesthetic judgments influenced his theoretical preferences. When forced to choose between beautiful circular models and accurate elliptical ones, he eventually prioritized empirical truth over aesthetic appeal. However, his discovery of harmonic relationships and the third law showed that nature sometimes did conform to human aesthetic ideals, making beauty a legitimate, though fallible, guide to truth. This raises philosophical questions about whether mathematical beauty and simplicity constitute genuine evidence for scientific theories or merely psychological preferences. Contemporary physics often invokes elegance and symmetry as criteria for theory evaluation, following Kepler's intuition that nature's fundamental structure should display mathematical beauty. But whether this reflects subjective features of reality or human cognitive biases remains contested among philosophers of science. Kepler's experience suggests that aesthetic intuitions can lead to discoveries when beauty aligns with truth, but must be overridden when they conflict with evidence. His treatment of anomalies and counter-evidence also demonstrated methodological maturity, recognizing that all theories face some contrary data without immediately being falsified. When harmonic ratios didn't match exactly or Platonic solids predicted slightly wrong distances, he attempted to modify auxiliary assumptions rather than abandoning core theories. This reflects what philosopher Thomas Kuhn later called normal science, where researchers protect theoretical frameworks by adjusting peripheral assumptions when anomalies arise. Only when modifications became too ad hoc or systematic discrepancies emerged did Kepler consider fundamental theoretical revision, showing sophisticated judgment about when to persist versus when to abandon theories. Kepler's Epistemology also contained explicit theological dimensions, grounding confidence in human cognitive access to natural truth through the doctrine of the divine image. Because humans possessed rationality reflecting divine rationality, human minds could comprehend the mathematical structure God embedded in creation. This theological foundation for epistemological optimism provided motivation for pursuing difficult investigations and confidence that natural laws existed to be discovered. Without such metaphysical grounding, skepticism about whether nature was rationally ordered might have prevented the sustained effort required for Kepler's discoveries. However, his theological epistemology also risked confirmation bias when religious convictions about cosmic harmony predisposed him to find harmonic patterns. The same metaphysical commitments that motivated discovery could also distort interpretation by encouraging perception of patterns that observations only weakly supported. Kepler's methodology was most successful when theological motivations drove empirical rigor, but didn't predetermine conclusions, allowing evidence to correct or refine religious expectations. His willingness to abandon circular orbits despite their theological appeal showed that empirical discipline could override metaphysical preferences when necessary. The relationship between Kepler's methodology and his discoveries raises chicken and egg questions about whether good methods produce good results, or whether successful scientists retroactively rationalize their practices. Kepler developed many of his methodological insights through the process of making discoveries rather than applying pre-existing procedures mechanically. His refusal to accept 8-minute errors was not following an established rule, but making a judgment call that observation quality warranted stronger theoretical constraints. This suggests that scientific methodology emerges through practice rather than being applied from philosophical principles, making methodology descriptive of successful science rather than prescriptive guidance. Kepler's extensive correspondence with contemporaries like Galileo, Brahe and Maestlin also reveals the social dimensions of his methodology, using dialogue to refine ideas. He sent manuscripts to colleagues for criticism, responded to objections by revising arguments and incorporated insights from others' work into his theories. This collaborative dimension of scientific practice contrasts with individualist myths about lone geniuses making discoveries in isolation. Kepler's achievements depended on access to Tycho's data, Galileo's telescopic observations, Gilbert's magnetic theory, and the broader intellectual community providing feedback and resources. His writing style in works like Astronomia Nova also demonstrated methodological transparency by documenting false starts, mistakes, and the reasoning process leading to discoveries. Rather than presenting only polished final results, he exposed his thinking process, showing readers how he arrived at conclusions through trial and error. This pedagogical approach made his work harder to read, but more valuable for understanding scientific reasoning as a process rather than just learning results. Modern scientific papers typically suppress this process, presenting findings as if they emerged directly from methods without detours or failures. Kepler's legacy for scientific methodology includes establishing that systematic discrepancies between theory and observation require theoretical revision, not just parameter adjustment. He showed that multiple independent measurements constrain theories more strongly than single observations by revealing systematic versus random errors. And he demonstrated that combining mathematical analysis, physical reasoning and empirical testing could yield both accurate descriptions and causal explanations of natural phenomena. These methodological contributions were as important as his specific discoveries for establishing standards that subsequent scientists followed. Part 9. Influence on Newton and the Scientific Revolution. Isaac Newton's Principia Mathematica, published in 1687, built directly upon Kepler's three laws by providing the theoretical foundation explaining why planets obey those specific patterns. Newton demonstrated that an inverse square gravitational force between masses necessarily produces elliptical orbits, area law motion, and the period-distance relationship Kepler had discovered empirically. This transformation of Kepler's phenomenological laws into derivable consequences of deeper principles represented a paradigm example of scientific progress through unification. Newton unified celestial and terrestrial mechanics by showing that the same gravitational force governing planetary orbits also caused apples to fall on Earth. The mathematical relationship was precise. Newton proved that any force decreasing as the inverse square of distance would produce conic section orbits following Kepler's area law. Conversely, objects following Kepler's laws must be subject to a central force inversely proportional to the square of distance from the centre. This mutual implication between Kepler's empirical laws and Newton's theoretical force law meant that Kepler's discoveries provided crucial empirical support for universal gravitation. Without Kepler's accurate description of planetary motion, Newton would have lacked the constraints necessary to identify the correct form of gravitational force. Newton's reformulation of Kepler's third law made it more general by incorporating the masses of both orbiting bodies rather than treating the Sun as infinitely massive. Kepler's version stated that period squared equals distance cubed for solar system planets, which works because planetary masses are negligible compared to the Sun. Newton showed that actually period squared equals distance cubed multiplied by the sum of the Sun's mass and the planet's mass, measured in solar masses. For planets, adding their tiny mass to the Sun's unit mass makes negligible difference, explaining why Kepler's simpler formulation was so accurate. However, this correction became crucial for systems where mass ratios are comparable, like binary stars or planet-moon systems, allowing astronomers to determine masses from orbital observations. Newton's version thus extended Kepler's law from a solar system-specific empirical regularity to a universal principle applicable to any gravitationally bound system anywhere. This generalization exemplified how Newton's theoretical framework absorbed Kepler's discoveries while expanding their scope beyond what Kepler had envisioned. The relationship between Kepler's work and Newton's raises questions about scientific credit and the continuity of scientific progress across theoretical revolutions. Should Newton receive primary credit for discovering the fundamental principles of orbital mechanics because he identified the underlying gravitational force? Or does Kepler deserve equal credit for discovering the precise mathematical laws that Newton's theory explained, without which gravity couldn't have been identified? The historical record suggests both contributed essentially but differently. Kepler provided empirical foundations and mathematical descriptions. Newton supplied theoretical unification and causal explanation. Newton himself acknowledged his debt to Kepler explicitly, stating that his own work built upon the foundations Kepler and others established. The famous metaphor about standing on the shoulders of giants, while directed at Robert Hooke in a backhanded way, aptly described Newton's relationship to Kepler. Newton's genius was synthesizing insights from multiple predecessors, including Kepler on planetary motion, Galileo on terrestrial dynamics, and Descartes on mathematical physics, into one unified theory. Without Kepler's accurate laws, this synthesis would have been impossible, because Newton needed precise empirical constraints to formulate universal gravitation correctly. Kepler's physical intuitions about solar force driving planetary motion also influenced Newton, despite being technically wrong in mechanism. Kepler established the research program of seeking physical causes for celestial motions rather than accepting geometric descriptions as sufficient. His proposal that force weakened with distance from the Sun, though incorrectly formulated as inverse linear rather than inverse square, pointed toward the solution Newton eventually found. Even Kepler's errors were productive by framing the right questions and demonstrating that physical causation could be quantified mathematically. However, Newton had to overcome several of Kepler's assumptions to arrive at universal gravitation, showing that scientific progress involves both continuity and conceptual transformation. Kepler's solar force was unidirectional, flowing from Sun to planets without reciprocal planetary forces affecting the Sun. Newton's third law of action and reaction required gravitational forces to be mutual, with planets attracting the Sun exactly as much as the Sun attracts planets. This mutuality meant the Sun itself orbits the solar system's center of mass, rather than remaining perfectly stationary as Kepler assumed. Kepler also believed forces required some quasi-material medium for transmission, whether magnetic fibers or species emanating from the Sun through space. Newton's gravitational force acted instantaneously across empty vacuum without any intervening substance, which Newton himself found philosophically troubling but mathematically necessary. This action at a distance violated Aristotelian and Cartesian requirements that forces must propagate through material contact or medium. Newton admitted he could not explain how gravity operated across empty space, but insisted that the mathematics demanded it, regardless of physical intelligibility. The progression from Kepler to Newton illustrates a pattern where empirical discoveries precede theoretical explanations by decades, requiring conceptual resources unavailable to initial discoverers. Kepler lacked the concept of inertia, which was necessary to understand why planets continue moving rather than requiring continuous pushing from solar force. He also lacked Newton's laws of motion, which were needed to relate forces to accelerations and derive orbital trajectories mathematically. Most crucially, he lacked calculus, which Newton invented precisely to solve the mathematical problems of planetary motion that Kepler's geometry couldn't handle. This temporal gap between discovery and explanation raises questions about what constitutes scientific understanding and whether phenomenological laws without causal explanation constitute genuine knowledge. Kepler's laws accurately describe planetary motion and enabled precise predictions, fulfilling practical goals of astronomy even without explaining why planets move that way. Did he understand planetary motion, or did understanding only arrive when Newton provided causal explanation through gravitation? The question highlights different conceptions of understanding, describing patterns versus identifying mechanisms versus deriving phenomena from fundamental principles. Kepler's contribution to the scientific revolution extended beyond his specific astronomical discoveries to methodological and metaphysical transformations in how natural philosophy was practiced. His insistence on mathematical precision, physical causation, and empirical accuracy over philosophical authority established standards that became definitive of modern science. The scientific revolution was not a single event, but a long transformation involving many contributors, with Kepler playing a crucial bridging role between Copernican astronomy and Newtonian physics. His work also exemplified the productive tension between metaphysical commitments and empirical flexibility that characterized successful science during this period. Kepler's Platonic conviction that nature was mathematically structured motivated his search for exact laws, yet he remained willing to modify specific mathematical assumptions when observations demanded it. This combination of metaphysical confidence in nature's rationality with empirical humility about human theories created an ideal epistemological stance for scientific discovery. Too much skepticism about finding patterns would have prevented systematic investigation. Too much confidence in particular theories would have prevented correction when wrong. The relationship between Kepler's religious motivations and scientific achievements also challenged secularization narratives portraying religion as obstacle to scientific progress. His Lutheran theology provided both motivation and conceptual resources for investigating nature mathematically, making scientific work a form of religious devotion. Without confidence that God created a rationally ordered cosmos accessible to human reason, Kepler might have accepted approximations rather than seeking exact mathematical laws. This suggests that the relationship between religion and science during the scientific revolution was more complex than simple conflict or independence, involving productive interactions where theological commitments enabled scientific innovation. Kepler's influence also extended to physics beyond astronomy, particularly in optics, where his work laid foundations for Newton's investigations of light and colour. Newton's experiments decomposing white light into colours and his corpuscular theory of light built upon optical principles Kepler had established in explaining refraction and image formation. The mathematical approach to understanding vision through geometry of light rays became standard methodology in physical optics throughout the 17th and 18th centuries. More broadly, Kepler helped establish mathematics as the language of natural philosophy, demonstrating that diverse phenomena from planetary motion to light propagation obeyed precise mathematical laws. This mathematization of nature became a defining feature of modern science, distinguishing it from qualitative Aristotelian physics based on verbal arguments. Galileo famously declared that the book of nature was written in mathematical language, an idea Kepler embodied through his actual practice of deriving exact numerical relationships from observations. The scientific revolution's transformation of cosmology from a finite, hierarchical cosmos to an infinite, uniform universe also owed much to Kepler's work. By showing that celestial motions obeyed the same physical principles that could be quantified mathematically as terrestrial phenomena, he undermined the ancient distinction between superlunary and sublunary realms. If planets moved through mechanical forces subject to mathematical laws, the heavens were not fundamentally different from Earth in kind, only in specifics. This homogenization of the cosmos prepared the ground for Newton's universal gravitation, which treated all matter identically regardless of celestial or terrestrial location. Kepler's legacy for the scientific revolution thus involved multiple dimensions, providing accurate empirical laws that constrained theoretical development, establishing methodological standards of precision and rigor, demonstrating mathematics' power for understanding nature, and beginning the conceptual transformation toward mechanistic natural philosophy. Newton's synthesis inherited all these elements, building upon Kepler's foundations to create classical mechanics as a complete theoretical framework governing all motion. Part 10. Legacy, Critiques and Modern Reassessment. Kepler's legacy divides sharply between his empirically successful astronomical discoveries and his metaphysical speculations about cosmic harmony that later science largely rejected. The three laws of planetary motion remain foundational to astronomy and physics, still taught in every introductory course and used for spacecraft navigation with only minor relativistic corrections. Meanwhile, his nested Platonic solids, musical cosmology, and astrological theories are remembered primarily as historical curiosities illustrating pre-modern thinking. This bifurcation raises questions about whether we should celebrate only Kepler's successes or understand his entire intellectual system as a coherent whole. Enlightenment historians of science treated Kepler's metaphysical and religious elements with embarrassment or condescension, viewing them as superstitious residues that he fortunately transcended through empirical discipline. Voltaire and other 18th-century writers portrayed Kepler as a great astronomer, despite his mysticism, implying that science progresses by shedding theological and aesthetic considerations for pure empiricism. This Whig interpretation presented scientific history as linear progress toward modern rationality, dismissing earlier frameworks as primitive stages to be overcome. Kepler appeared as a transitional figure caught between medieval superstition and Enlightenment reason, valued only for discoveries that survived into modern science. Romantic natural philosophers in the 19th century reversed this assessment, celebrating Kepler precisely for his holistic vision unifying science, art and spirituality. William Whewell's influential History of Science portrayed Kepler as the archetype of inductive genius, combining aesthetic sensibility with mathematical rigour. Ernst Appelt's study of Kepler's manuscripts emphasized that his mathematics, theology and aesthetic ideas formed a unified system of thought rather than separate compartments. This romantic rehabilitation viewed Kepler's metaphysical commitments as enabling rather than hindering his scientific achievements, providing conceptual resources for revolutionary discoveries. Alexandre Koyrè's 20th century work continued this interpretive tradition, arguing that Kepler's Platonic metaphysics was essential to his astronomical revolution rather than incidental mysticism. Koyrè emphasized Kepler's theoretical creativity over his empirical work, placing theorization at the center of the scientific revolution's intellectual transformation from ancient to modern worldviews. This interpretation challenged positivist historiography that separated factual discoveries from metaphysical contexts, showing that philosophical frameworks shaped which empirical patterns became visible to investigators. Contemporary historians of science generally adopt more nuanced views, recognizing that Kepler's metaphysical beliefs both enabled and constrained his discoveries in complex ways. His theological conviction that God created a rational cosmos motivated the search for exact mathematical laws with unprecedented rigor. But the same conviction that creation must embody harmonic beauty led him to see patterns in planetary velocities that observations only weakly supported. Rather than judging metaphysics as purely helpful or purely harmful, modern scholarship examines how specific beliefs function differently in different investigative contexts. One major critique of Kepler concerns his willingness to tolerate larger discrepancies in harmonic relationships than in orbital calculations, suggesting motivated reasoning. For the planetary laws, he rejected 8-minute errors as unacceptable. For cosmic harmonies, he accepted deviations of several percent through auxiliary hypotheses. This apparent double standard reveals that empirical rigor was not absolute, but varied depending on how strongly prior commitments constrained acceptable results. Where physical motion was concerned, independent observational data forced accuracy. Where aesthetic harmonies were concerned, theological expectations influenced interpretation. Another critique addresses Kepler's failure to discover universal gravitation, despite coming tantalizingly close conceptually and mathematically. He recognized that some force from the Sun moved planets, and that this force weakened with distance, yet formulated the distance relationship incorrectly as inverse linear rather than inverse square. Some historians argue this failure resulted from inadequate mathematical tools, particularly lacking calculus to derive orbital trajectories from forces rigorously. Others suggest conceptual barriers prevented the breakthrough. His commitment to circular motion in the early work, his focus on tangential pushing force rather than radial attraction, and his belief that forces required material transmission. However, expecting Kepler to have discovered universal gravitation may be anachronistic, requiring conceptual resources that only became available through subsequent developments. The concept of inertia, clarified by Galileo and formalized by Newton, was necessary to understand why planets continue moving without continuous pushing. Newton's laws of motion provided the framework relating forces to accelerations that Kepler lacked entirely, and the mathematical techniques of calculus, which Newton invented partly to solve these problems, were indispensable for deriving elliptical orbits from inverse square forces. The discovery of Uranus in 1781 and Neptune in 1846 decisively refuted Kepler's Mysterium Cosmographicum model by adding planets beyond the 6 Platonic solids could accommodate. His geometric explanation for why exactly 6 planets existed became obviously wrong, once observation revealed 7th and 8th planets. This falsification demonstrated the empirical character of his nested polyhedra hypothesis, which made definite predictions that observations could test. Unlike unfalsifiable metaphysical speculations, Kepler's geometric cosmology was vulnerable to refutation, showing that even his most mystical-seeming ideas had empirical content. Yet the Mysterium Cosmographicum's failure raises interesting questions about scientific creativity and the value of false but fruitful hypotheses. Although the specific model was wrong, it motivated Kepler's astronomical work and led to the search for mathematical relationships in planetary orbits. The third law emerged partly from seeking harmonic proportions that the polyhedral model couldn't fully explain, showing that false theories can guide toward true discoveries. This suggests that evaluating past science only by current truth standards misses how incorrect frameworks function productively during investigation. Kepler's harmonic cosmology similarly failed empirically. Planetary velocity ratios do not form precise musical intervals, and the claimed relationships involve too much interpretive flexibility. Modern recalculations show that some ratios are several % away from the claimed musical intervals, beyond what measurement error could justify. The Mars-Jupiter velocity ratio produces no consonant interval at all, creating an awkward gap in the harmonic system. Kepler's explanations for these discrepancies through orbital adjustments needed to fit Platonic solids were ad hoc, protecting the theory by introducing auxiliary hypotheses without independent justification. Yet dismissing the harmonic project entirely may overlook genuine insights about seeking mathematical patterns underlying natural phenomena. Contemporary physics continues to seek symmetries, conservation laws, and mathematical elegance in fundamental theories, following Kepler's intuition that nature's deep structure displays mathematical beauty. String theory proposes that particles are vibrations of fundamental strings, explicitly invoking musical metaphors reminiscent of Kepler's cosmic harmonies. While the specific harmonic claims failed, the broader methodological approach of seeking mathematical patterns and aesthetic unity in physical laws remains central to theoretical physics. Kepler's astrological work has been almost universally rejected by modern science as empirically unfounded and conceptually confused. No reliable correlations exist between planetary aspects and terrestrial events. Weather patterns depend on atmospheric physics, not celestial configurations. The psychological mechanism Kepler proposed, where souls respond to geometric harmonies formed by planets, lacks any empirical support from neuroscience or psychology. Human cognitive responses to visual patterns and musical intervals operate through neural mechanisms unrelated to astronomical positions. Nevertheless, his attempt to reform astrology on naturalistic principles illustrated scientific approaches to evaluating traditional beliefs rather than merely accepting or rejecting them wholesale. By proposing testable mechanisms for astrological influences and restricting claims to what geometry could justify, he treated astrology as a natural phenomenon requiring scientific investigation. The investigation concluded negatively, but conducting it rigorously was itself methodologically valuable, demonstrating how empirical testing could assess traditional wisdom. This contrasts with simply dismissing astrology as superstition without examining whether any version might be defensible. Modern reassessments of Kepler also consider his influence on the development of science as a professional discipline with specialized training and institutional structures. As imperial mathematician, Kepler occupied an official position dedicated to astronomical work and calendar calculation, representing early professionalization of scientific roles. His extensive publications established models for communicating technical research to specialist audiences through mathematical arguments and empirical evidence. The Rudolphine tables demonstrated how scientific work could produce practical resources with economic value, justifying continued support for astronomical research. Kepler's correspondence network with astronomers and natural philosophers across Europe also contributed to emerging scientific communities where researchers shared findings and critiqued each other's work. This collaborative dimension of scientific practice, though informal compared to later institutions like the Royal Society, established patterns of peer review and collective knowledge building. His willingness to expose his reasoning process in published works made scientific methodology itself an object of study and discussion, helping to codify standards for scientific argument. The question of Kepler's overall significance for the history of science depends partly on whether we emphasize continuity or discontinuity in scientific development. If science progresses through cumulative addition of empirical discoveries, Kepler's three laws represent his main contribution, which Newton absorbed and explained more deeply. If science advances through conceptual revolutions, where new frameworks replace old ones, Kepler's transformation of astronomy from geometric description to physical explanation marks him as revolutionary. If science develops through complex interactions between theory, observation, and metaphysics, then Kepler's entire intellectual system, including its failures, becomes historically significant. Contemporary philosophy of science continues to debate issues Kepler's work raises about the role of metaphysical commitments, aesthetic criteria, and religious beliefs in scientific reasoning. The demarcation problem of distinguishing science from non-science becomes difficult when examining historical cases where successful scientists held beliefs now considered unscientific. Kepler believed in cosmic harmonies and astrological influences while making revolutionary astronomical discoveries. Were these separate aspects of his thinking or integrated parts of one framework? Different answers to this question reflect different theories about science's essential characteristics and how it differs from other intellectual activities. Kepler's legacy also includes ongoing influence on how we teach the history and nature of science to students and the public. Textbooks typically present his three laws as straightforward empirical discoveries without discussing the metaphysical context from which they emerged. This simplified presentation serves pedagogical purposes by focusing on content that remains scientifically valid, but it may distort understanding of how science actually develops. More historically accurate presentations would show how theological and aesthetic commitments motivated the search for precise laws, raising uncomfortable questions about science's relationship to non-empirical beliefs. The broader cultural legacy of Kepler's work extends into art, literature and music, where his harmonic cosmology inspired creative works long after scientific rejection. Composers have set his celestial harmonies to music. Science fiction writers have explored his ideas about living cosmos. Visual artists have depicted his geometric models. This cultural resonance suggests that Kepler's vision of a beautiful, harmonious universe structured by mathematics speaks to human aesthetic and spiritual needs beyond its scientific truth value. Whether science should acknowledge and incorporate such non-empirical values or rigorously exclude them remains philosophically contested. Finally, Kepler's life and work raise questions about the relationship between personal suffering and intellectual achievement that resist easy answers. He endured religious persecution, forced relocations, family tragedies including children's deaths, his mother's trial for witchcraft, and chronic poverty despite official positions. Did these hardships drive his intense focus on astronomical work as refuge from painful reality, or did they impede discoveries that would have come faster under better circumstances? The romanticized view of suffering artist or scientist finds little support in Kepler's case. His achievements emerged despite rather than because of his suffering, though adversity may have strengthened his character and determination. His legacy ultimately rests on having fundamentally transformed humanity's understanding of the cosmos through mathematical precision, physical insight, and methodological rigor. The three laws of planetary motion, optical theory of vision, and contributions to scientific methodology remain lasting achievements regardless of how we assess his failed speculations. Yet understanding Kepler fully requires grappling with his entire intellectual system, including elements modern science rejects, because that system generated the insights we still value. He stands as a towering figure in the scientific revolution, whose complex blend of mysticism and mathematics, theology and physics continues to challenge simplistic narratives about how science develops and what enables revolutionary discoveries.